y'all. Good morning, good morning. All right, we are going to continue talking about momentum, but today we're going to be talking about the conservation of momentum. So I've kind of split this into two parts. It was all put together, but I did split it in two. So whenever we're talking about conservation of momentum today, I want you to begin thinking about, about collisions. Okay, things colliding with each other. All right, so let's continue, or let's get started. All right, so let's take playing pool, for example. All right, so whenever you play pool, you strike the cue ball, and it hits one of the other balls that are not moving. Okay, so that cue ball, say it hits the 8 ball. Well, the 8 ball was not moving before the cue ball hit it. Okay, and we learned the other day that if you are not moving, then you have no momentum. Okay, so all of the momentum in this collision is beginning with that cue ball. All right, that's the only momentum that is present because the 8 ball has no momentum to start with. Well, whenever that cue ball strikes the 8 ball, you can have a couple of different things that happen. Okay, that cue ball can completely stop and the 8 ball will continue moving. Well, the 8 ball, once again, was not moving before. So where the heck did it get its momentum? It got it from the cue ball. All right, so if the cue ball stops moving altogether, then that means that the 8 ball took every single bit of its momentum. If the cue ball continues to move a little bit and the 8 ball starts moving as well, then the cue ball only transferred a portion of its momentum to the 8 ball. All right, so the same amount here, we'll highlight this. The same amount of momentum that the cue ball loses is the amount of momentum that the 8 ball gains. All right, and this is called the conservation of momentum. All right, so this is very, very similar to the conservation of kinetic energy or energy period. All right, so the energy at the beginning is the same, or the total energy at the beginning is the same as the energy at the end. We saw that where we had, here, I'll write it on here, where we had GPE initial plus KE initial is equal to GPE final plus KE final. Well, we saw this. We saw several things where there was both gravitational potential and kinetic at the beginning, and then it all turned into kinetic at the end. We saw it where all of the initial energy was gravitational potential and it all turned into kinetic energy at the end, that kind of thing. All right, so we're looking at a similar concept. So whenever you have a collision, that's what it means by interacting. All right, so whenever objects interact with each other, whenever they collide with each other, the momentum, the total momentum, remains constant. All right, so it remains constant regardless of the nature of the forces between the objects. All right, so just like we had the conservation of energy, okay, we had that, we'll write it again, GPE initial plus KE initial is equal to GPE final plus KE final. Well, we broke that down into MGH initial plus 1/2 MV initial squared is equal to MGH final plus 1/2 MV final squared. Okay, so you have already seen this breaking down of these equations. All right, so here we're looking at two different objects, no longer looking at just one object. We're looking at two different objects colliding with each other. So we have to take both of their initial momenta and then both of their final momenta into account. All right, so if we didn't break this down, so this is the broken down version. So what we would be looking at was the initial momentum of the first object plus the initial momentum of the second object is equal to the final momentum of the first object plus the final momentum of the second object. All right, so that is what has been broken down for you here. All right, so you have the mass of the first object times the initial velocity of the first object plus the mass of the second object times the initial velocity of the second object is equal to the mass of the first object times its final velocity, and then the mass of the second object times its final velocity, okay? But what you need to remember just overall is the total initial momentum has to equal the total final momentum. The total initial momentum is equal to the total final momentum. All right, and at this time, if we were in person right now, I would bring out my Newton's cradle. All right, so everyone knows what a Newton's cradle is. If I were to pull this one back and let it go, then all of that energy would be transferred through these, and then this one would move up. All right, if I did 2 at the beginning, then 2 would come up this way. If I did 3, then 3 would come up this way. All right, so what that is showing is the conservation of momentum. All of the momentum of this first one was transferred to this last one and made it move. All right, so once again, the total momentum of all objects, remember, interacting with each other just means colliding with each other. All right, so whenever they are colliding, then energy is momentum, the total momentum is conserved. All right, so if we go back to our initial example of the cue ball hitting the 8 ball. Now, the cue ball and the 8 ball had very different momenta to start off with and very different momenta to end with, but the total amount of momentum was constant. All right, so say we had the cue ball. So the initial momentum of the cue ball plus the initial momentum of the 8 ball was equal to the final momentum of the cue ball plus the final momentum of the 8 ball. So this was 0 to begin with, and we'll say that the cue ball completely stopped at the end. That would mean that this was 0. So all of the initial momentum that the cue ball had was transferred to the 8 ball at the end. Okay, so we're going to be talking about this a lot. This is just bringing in kind of connecting what we did last unit with kinetic energy, or the conservation of energy and momentum. All right, so let's take objects that are pushing away from each other. Okay, so that means that they are going in opposite directions. Okay, if they are pushing away from each other, then they are going in opposite directions. All right, so we've talked about Newton's third law. All right, Newton's third law said that for every action force, there is an equal and opposite reaction force. All right, so that explains that we're going to be getting into this in just a second as well, but Newton's third law helps to explain the conservation of momentum. Okay, so if you have something that is pushing away from something else, so say you jump up, you push off the earth. Okay, so you're going up, the earth is technically going down. So take your mass and velocity. All right, so let's say that your momentum as you're going up is 60 kilogram meters per second upward. Well, we know that that means that the earth has to have an equal but opposite momentum. All right, so the earth's momentum is also 60 kilogram meters per second, but it's going downward. Okay, so your total momentum, so you started off, both of you started off on the ground. So both of your initial momenta was zero. Okay, there was no movement. And then you pushed up, which made you have a velocity. Now, the big difference is that your mass is minuscule compared to the Earth's mass. All right, Earth has an enormous mass, so that means that its velocity is super, super small. All right, so you would not really even notice any sort of change. And we talked about this. All right, so we talked about the force being mass times acceleration. This is where we talked about it with Newton's third law. So the amount of force that we are pushing off of the earth with is equal to the amount of force that the earth is pushing off of us with. But because the masses are completely different, like our mass is super small, which means our acceleration is a lot larger than what the earth's acceleration is. All right, it's the same thing with momentum. All right, so we have that equal and opposite. So equal and opposite momentum. But if you're looking at velocity, if you have a huge mass, then that means that your velocity is going to be teeny, teeny, tiny. All right, so the momentum is going to be the same, but your mass and velocities are not. All right, so let's take these two people. All right, so these people are on skates. They are on ice skates. Okay, so they don't necessarily have to be the same mass. All right, they could be. We can use the same mass for this one. All right, so they push away from each other. So if they're pushing away from each other, then they're going in opposite directions. All right, but if you look right here, they're not moving. So the initial momentum for both of them is going to be zero. All right, so their initial momentum is going to be zero. Now, as they push off of one another, then this momentum is going to be negative. This momentum is going to be positive. All right, so they are going to be equal and opposite, which means their final momentum is still zero. Their final momentum is still zero. Okay, now we said that they had the same mass. So if they have the same mass, then they're going to have the same velocity. It's just going to be in the opposite direction. But what if this one had a greater mass? What does that mean her velocity is going to be? If the momenta, are the same and her mass is larger, that means that her velocity is going to have to be smaller. Okay? So hopefully we understand that. All right, now this one is a big one. So we just said this. So Newton's third law leads to the conservation of momentum. So for every action force, there's an equal and opposite reaction force. Okay, so here we have Newton's first law. Newton's first law is all about inertia. We talked about inertia in our introduction to momentum and collisions. So inertia is an object's resistance to a change in motion. So if an object is already in motion, it is going to want to stay in that motion. It's not going to want to slow down. It's not going to want to speed up. It's not going to want to change direction unless it is acted upon by an outside unbalanced force. All right, so Newton's first law is definitely leading us to inertia. Newton's second law which we saw broken down in our car crashes video, is leading us to the the impulse momentum theorem. Leads us to the impulse momentum theorem. All right, so it was just a rearranged equation. All right, so Newton's second law rearranged gives us the impulse momentum theorem. We saw that in the video. And then Newton's third law helps us to explain the conservation of momentum. I would write these down. You might see these later. Okay, so because we know that there are equal and opposite forces, all right, so the forces exerted cause a change in momentum for each car. Now, we talked about like the bug hitting the windshield. All right, the bug and the windshield are both experiencing the same force, but the bug with a smaller mass experiences a greater acceleration. It's the same thing for momentum. They might be experiencing the same momentum, but the larger mass is going to experience a smaller velocity, a smaller change in velocity. All right, but what you see is going to be the exact same. So your momentum, your initial momentum, your total initial momentum is still going to equal your total final momentum. All right, so let's put that into an example. All right, so we have a 76 kilogram boater initially at rest in a stationary 45 kilogram boat, steps out of the boat onto the dock. If the boater moves out of the boat with a velocity of 2.5 meters per second to the right, what is the final velocity of the boat? All right, so let's get all of our givens written out. Okay, so we have our boater. We're going to put him as mass number 1. Okay, I put in an extra slide on here so that I could have space to work this out. All right, so our first mass is going to be our boater. He is 76 kilograms. Now, it says that he was initially at rest. So V1 initial, the initial velocity of our first object, is 0. Now, it also says that he was in a stationary boat. What does stationary mean? That means that it is not moving as well. So the initial velocity of our second object, so V2 initial, is also 0 meters per second. All right, and then we've got our second object, which is our boat. So we've got M2, which is 45 kilograms. Okay, so this is everything we need to figure out our initial momentum, okay? And hopefully you're kind of looking at it already and seeing that because both the boater and the boat itself were both at rest, then our initial momentum was 0. So that means that our final momentum has to also be 0. So let's figure all this out. All right, so the boater gets out onto the dock and he has a final velocity of 2.5 meters per second to the right. We want to know what is the boat's velocity. What is the boat's final velocity? All right, so we know that momentum is going to be conserved. All right, so that means that M1 times V1 initial plus M2 V2 initial is equal to M1 V1 final plus M2 V2 final. Okay, so hopefully right now you see that V2 initial and V1 initial are both 0. So both of these are 0. So our initial momentum is 0. So now we can plug in for our final momentum. All right, so mass 1 is 76. Its final velocity is 2.5 meters per second to the right, plus our second mass, which is 45, times V2 final. All right, so we have 0 is equal to 76 times 2.5. All right, I guess we could have rearranged. Yeah, let's rearrange before we plug in. I mean, you could do it either way. I just like rearranging. All right, so we have 0 is equal to M1 V1 final plus M2 V2 final. All right, and we're solving for V2 final. So the first thing that we're going to get rid of is this whole piece right here. They're all together. All right, and it's being added to that second piece. So the way to get rid of it would be to subtract it. So 0 minus M1 V1 final is equal to M2 V2 final. So still trying to solve for V2 final, we need to divide both sides by M2. All right, so now we know that V2 final is equal to 0 minus M1 V1 final over M2. So now we can plug in those numbers. So we have 0 minus our M1 is 76 times V1 final, which is 2.5 to the right, over our second mass, which is 45. Okay, so that gives us, if we plug it in, that gives us a negative 4.2 meters per second, or 4.2 meters per second to the left. And that should make sense that it's to the left or negative, because whenever the boater moves out and moves to the right, that force is going to make the boat travel in the opposite direction, so left or in the negative direction. Okay, so I hope that one was pretty easy for you. Let's try another one. Okay, so we have a 63-kilogram astronaut is on a spacewalk when the tether line to the shuttle breaks. The astronaut is able to throw his spare 10-kilogram oxygen tank in the direction away from the shuttle with a speed of 12 meters per second, propelling the astronaut back to the shuttle. Again, there is Newton's third law of motion in work right there. Assuming that the astronaut starts from rest with respect to the shuttle, find the astronaut's final speed with respect to the shuttle after the tank is thrown. Okay, so we kind of have to think about what's happening here. So the astronaut has this oxygen tank on his back. This oxygen tank is not just floating around randomly in space, all right? It's on his back. All right, so we've got our first mass. Let's write down our givens first. All right, so we've got our first mass. It's the mass of the astronaut. That's our first object, is 63 kilograms. Okay, he has a second object, which is that 10-kilogram oxygen tank. Now, he was at rest. So if he was at rest, the oxygen tank that was on his back was also at rest to begin with. So V1 initial is 0 meters per second, and V2 initial is 0 meters per second. Okay, now, he throws the tank away from the shuttle. So everything that we are doing is with respect to the shuttle. So if he's throwing it away from the shuttle, then the oxygen tank's final velocity is going to be a negative. That negative tells us that it's going away from the shuttle with a velocity of 12 meters per second. I want to know what the final velocity of the astronaut is. All right, so we know that because of Newton's third law, equal and opposite forces, that momentum is conserved. All right, so momentum is conserved. So we have M1 V1 initial plus M2 V2 initial is equal to M1 V1 final plus M2 V2 final. All right, once again, both of our things started at rest. So our initial momentum is 0. So that's M1 V1 final plus M2 V2 final. This time, we're looking for V1 final. So first thing we have to get rid of is this whole piece right here. That sticks together. All right, so it's being added, so we subtract. So 0 minus M2 V2 final is equal to M1 times V1 final. And now to get rid of M1, we just divide. All right, so V1 final is equal to 0 minus M2 V2 final all over M1. We have all of this, so we can just go ahead and plug it in. So 0 minus M2, which is 10, times V2 final, which is negative 12, all over M1, which is 63. Okay, so that's going to be a 0 minus a negative 120. What is that going to give us? That's going to give us a positive. So 120 divided by 63 is going to give us a positive 1.9 meters per second. So that positive tells us that the astronaut was traveling towards the shuttle. So remember, everything was in respect or with respect to the shuttle. So that positive tells us that it's going towards the shuttle with a velocity of 1.9 meters per second. Okay, last but not least, each croquet ball in a set has a mass of 0.5 kilograms. The green ball, traveling at 12 meters per second, strikes the blue ball, which is at rest, assuming that all collisions are head-on. So they're all coming at each other. Find the final speed of the blue ball in each of the following situations. All right, so we are looking for V2 final for all of these. It's the final velocity of the blue ball. All right, so we know that our masses are the same. The mass of the green ball is 0.5. The mass of the blue ball is also 0.5 kilograms for both of those. All right, we found that right there. All right, and then the V1 initial is equal to 12 meters per second. Okay, so that's for all of these. So the only difference, and then V2 initial, is equal to 0. All right, so our initial momentum is the exact same for all of these. Okay, so all of our initial momentum is coming from that green ball. So if we want to solve for it, we can. All right, so just to make it easier, well, what do y'all want to do? Let's see, what's going to be the easiest way? I'll just do it all for this first one. We'll just do it like normal. Okay, so for this first situation, the green ball stops moving after it strikes the blue ball. All right, so that means that V1 final is equal to 0. All right, I'm going to bring this down here. This is why I put an extra slide here. All right, so for A, we know M1 is 0.5 kilograms. M2 is also 0.5 kilograms. V1 initial is 12 meters per second. V2 initial is 0 meters per second. And all of that we got from our problem up at the top. Now we are looking for, we were told that the green ball stops moving. So V1 final is equal to 0, which means we're looking for V2 final here. All right, so we know M1 V1 initial plus M2 V2 initial is equal to M1 V1 final plus M2 V2 final. All right, we're solving for V2 final for all of these. Now, for all of these, this one is 0. So our initial velocity is m1 v1 initial, but our v1 final for this one is also 0. So m1 v1 initial is equal to m2 v2 final. So easy peasy, we'll just divide both sides by m2. So v2 final is equal to m1 v1 initial over m2. So we have our mass, which is 0.5, times v1 initial, which is 12 over 0.5, which is going to give us a velocity of 12 meters per second. All right, so it's going to be traveling 12 meters per second. So the green ball, that should make sense because the blue ball took every single bit of momentum from the blue ball that it initially had, because the green ball is what you start off with, the blue ball is what you end with. All right, so the green ball was the one that was moving at the beginning. The blue ball was not. The green ball hit the blue ball. The green ball stopped moving. The blue ball took all of the momentum. So, of course, it's going to have the same velocity as what the green ball had at the very beginning. All right, so let's try the second one. All right, the green ball continues moving after the collision at 2.4 meters per second in the same direction. Okay, so instead of having a V1 final of 0, we now have a V1 final of 2.4. Okay, so let's do this. So we have M1 V1 initial plus M2 V2 initial is equal to M1 V1 final plus M2 V2 final. And again, solving for that, this is still 0. Now, for this one, that's the only one that's 0. So we have M1 V1 initial is equal to M1 V1 final plus M2 V2 final. So let's rearrange. Let's get rid of this whole thing. So we're going to subtract that from both sides. So we have M1 V1 initial minus M1 V1 final, and that's all over M2. That's going to give us V2 final. Okay, so M1, 0.5, times V1 initial, which is 12, minus 0.5, times V1 final. What was V1 final here? 2.4. All over 0.5. Let's work that out. So 0.5 times 12 is going to be, that's 6, right? Minus 0.5 times 2.4, is that 1.2? Yes? Yes? Right? No? Yes? Yeah. Yeah. I'm losing my mind. Over 0.5. So that's going to be 5. Lord have mercy. Where's my calculator? I can't do simple math. Okay, 6. That's 4.8. Oh my gosh, I'm losing my mind. All right, so 4.8 divided by 0.5. I really do need it for this. So 4.8 divided by 0.5 is going to give me 9.6 meters per second. And it's going in that same direction. Okay, so let's look at this. So this is the green. No, blue. Lord have mercy. If I can keep these straight, that would be great. All right, so this is the final velocity of the blue ball. Okay, because this was the initial velocity of the green ball. This was the final velocity of the green ball. Okay, so we know that all of the momentum came from the green ball. All right, so they both have the same masses. So all of the velocity was 12. So what do you notice 2.4 plus 9.6 is? It's 12. I know. What a coinky-dink, don't you think? It's not a coincidence at all. All right, so the green ball, let's do this last one. The green ball continues moving at 0.3. So this is V1 final. All right, so that's the final velocity of the green ball there. We're trying to find the final velocity of the blue ball again. Okay, so we know that M1 V1 initial plus M2 V2 initial is equal to M1 V1 final plus M2 V2 final. Again, solving for V2 final, we know that this is 0 because it's not moving. Okay, so M1 V1 initial minus M1 V1 final over M2 is equal to V2 final. So we have M1, 0.5, times V1 is 12, minus 0.5, times V1 final, which was 0.3, over 0.5. Okay, this is going to be 6 minus 0.5 times 0.3. Why do I have to do this? 0.5 times 0.3. 0.15. Oh my gosh, why did I not get that? I'm an idiot. All right, so 6 don't judge me. 5.85 over 0.5. We should get 11.7 meters per second, which should make sense because 11.7 meters per second plus 0.3, which is the final velocity of the green ball, gives us 12, which is the initial velocity, all right, of the entire thing. All right, so hopefully this makes at least a little bit of sense. We are going to cover collisions next, the different type of collisions, and that's going to bring in this conservation of momentum a little bit more. All right, but just remember that momentum is conserved. Total momentum is conserved. And we'll be doing more practice and more notes with this. But if you have any questions, write them down and let me know.